Now the next section that I'm moving into has to do with differential equations, and being able to solve differential equations is an important skill for a physics student and for an engineering student. So please pay attention. This is actually one of the most mathematically challenging subjects in AP Physics C, and you will see a lot of this in E&M, which I can't wait to start. So pay attention. I'm actually on page 359 of the textbook. As of this moment, we have talked about friction, and one of the distinguished features of friction between two solid surfaces is that it does not depend on the relative velocity between the two surfaces, neither does it depend on what? The surface area. We said that friction depends on the nature of what? Surface, and on the normal force that the surfaces exert on each other. But this is only true for solid surfaces. You will encounter situations in which a solid surface is moving on what? A semi-fluid surface, or in a fluid such as air or water. In that case, the friction force experienced by the object will depend on the relative velocity of what? That object on that surface or through the fluid. So it is critical for you to understand this topic because it's a very popular topic for AP Physics C. Literally, if I count the number of questions from 1990 to 2015, a question was given in this particular section in 1990, 93, 99, 2008, 2011, 2013, and throughout these years in the multiple choice, there are always questions. So I think it's an area for you to pay attention on. And secondly, we will encounter differential equations. You should not develop anxiety now because of it. Most of the differential equations that we will solve will be first order differential equations. And I'm going to show you a trick or a method whereby you can actually separate the variables and solve this as simple word integrals. So let's get rolling. Take for example, let's consider drag racing, for example. Usually the cars are designed to run at very high velocities, above 100 miles per hour, and therefore braking is an issue. The brakes installed in the cars are insufficient to what? Completely stop the car at the time the car wants to be stopped. So as a result, parachutes are used. Let's assume that the car is initially traveling with a speed V0 when the parachute is deployed. And due to the presence of the parachute, what happens is that air exerts a backward resistive force F equal to kV, proportional to the speed of the car. So the question is, we're interested to derive the expression of how the acceleration, the velocity, and the position of the car varies during that limited period that the car is braking. Now, the very first step in solving this kind of problems is to, first of all, draw the free body diagram. Remember that the friction due to air outweighs the friction due to the surface. So we are going to totally ignore the friction on the surface. So if we do the free body diagram, we will have a force downwards. This is mg. Normally, the normal force is acting on the tires. This is N, and there are 4, so there are 4. But I'm going to just put a total N here. And there is a force backwards, which is Fk. So if I draw the free body diagram here, we will have, this is mg, that is N, and this force here is Kv. There is no force acting forward because the car is decelerating. But remember that this is the direction of motion. Now, that being said, if we apply the forces in the y direction, we will have N minus mg, which is equal to 0. This means that N is equal to mg. Now, if we apply the forces in the x direction, this is equal to ma, which implies that we have 0, there is no force in the forward direction, minus kv will be equal to ma. Now, this will give us negative kv equal to m dv dt. This is a first order differential equation which we can easily solve. If we separate the variables, we will have here negative k over m dt, all of this equal to what? dv over v. We are integrating. This is, pardon?
ln.
Yep. As easy as that. Now, if we integrate from 0 to t, from v naught to v, we are going to have here the natural log of v from v naught to v equal to negative kt over m.
I have a question.
Yes, please.
How come it's not absolute value?
Yep. We can put the absolute values. In math, it's important. In physics, it's really not that important.
Okay.
So, we will have here the natural log of v minus v naught equal to negative kt over m, which basically implies that v is equal to v naught raised to the power kt over m. That's all right. He's putting the phone off, and that's very responsible. And thank you for doing that. Now, please, sorry about that. We have derived an expression for how the speed of the car varies with time. We just proved that v is equal to v naught e negative kt over m. Remember, v is equal to v naught e raised to the power kt divided by m. Now, what is the value at t equal to 0? At t equal to 0, this will be negative what? K over m multiplied by 0, and this will be equal to v naught, right? Now, what about v at infinity? Remember that the limit of v as t approaches infinity is just the limit. This is v naught all divided by e raised to the power kt over m as t approaches infinity. As t approaches infinity, this thing approaches what? 0. Therefore, if we draw our graph will look somewhat like this. That is V. This is V naught. And that will be our graph. The next step that we have to take, A is equal to dV over dt, which will be equal to what? V naught bracket negative K over M. Is it K over M? Yep. E raised to the power negative KT over M. This will be equal to negative KV naught over M E raised to the power negative KD over M. So if we draw the graph of A against...
This is for you. It's a kindness gram.
Thank you.
There's candy inside.
Oh, that's so sweet. That's really so nice. So if we look at this critically, look up everybody. The value of A at t equal to 0 is equal to what? Negative kV naught over M. Now, as t approaches infinity, A approaches 0. So if we draw our graph, it's gonna be interesting. This graph that we are drawing, I didn't draw this in the textbook, but it will be in the updates that you will receive in a week from now. So the graph will look like that, inverted. And it will be in the physical copy, whoever gets it. So we have V equal to V naught E negative KT over M. We know that V is dx over dt. This therefore implies that dx over dt is going to be equal to V naught E negative KT over M. And therefore dx will be equal to V naught E negative KT over M dt. If we integrate from x naught to x, now we are going to assume that the object is initially at the origin later, and we're integrating from 0 to t. We will have x minus x naught, all of this equal to what? V naught bracket k, now the opposite, V naught bracket negative M over K E negative KT over M, and we're integrating from 0 to t. Initially the guy is at the origin, so x will be equal to negative V naught M over K bracket E negative KT over M minus 1, which can still be rewritten as, this would mean that x is equal to V naught M divided by K bracket 1 minus E raised to the power KT over M. So that is the expression for x. There will be one of these in the exam. Trust me. There will be 2 questions in the free response, as usual. One in velocity-dependent forces, and one involving inclined planes and coupled objects. So Practice. Practice. And if there is a tie on the first place, I'll give a tiebreaker for the person who will earn the textbook. And it's an expensive book, so that's a good price. And if I give the tiebreaker and they still have 100%, then all of them will get a book for free. Look up, everybody. We have x equal to mv naught over k bracket 1 minus e negative kt over m. What you need to realize that at t, x naught is equal to what? mv naught over k. Now, as t approaches infinity, now, am I missing something? X naught should be 0. Sorry. Let's look at some critical values here. Please look up. Whenever you derive an expression like this, always analyze some important values like what is the value of that quantity at t equal to 0 and what is the value of that quantity at t equal to infinity. These are called the endpoints, and it often gives you the physical limitations of what the system. So at t equal to 0, x of 0 will be equal to what? mv naught over k 1 minus 1, which is 0. Which makes sense because at t equal to 0, the object is where? At the origin. Now, at x infinity is equal to, at infinity, this thing turns to what? 0.
Wait.
Now, look at it as t approaches infinity, e raised to the power kt over m approaches 0. And to see that, remember, this guy can be rewritten as e kt over m. As t approaches infinity, the denominator approaches infinity and the fraction approaches 0. Therefore, we now have here mv naught over k. So if we draw a graph of x against t, it will be, this is mv naught over m. It's gonna be like that. It's gonna be like that.